This lecture we will prove the general case of the Goursat theorem. So first, we state and prove corollary to Goursat theorem for the special case. Also, starting from Goursat theorem, we are discussing chapter 2 of Stein's book. In case you want to know where to get some problem set to work on. Corollary to Goursat's theorem for the special case of integrals over boundary of rectangle. So let U be a simply connected open subset of C, and Fz be a holomorphic function on omega. Then there exists a holomorphic function capital Fz on U, so which is known as a parameter of Fz on U, whose complex derivative is Fz. Okay, so we make some remark. First remark, so how we use simply connectedness. So the simply connectedness of the domain U guaranteed that any continuous loop inside U can be continuously shrunk inside U to a point in U. In particular, it implies that two polygonal pairs inside U joint to points in U with only horizontal and vertical sides can be transformed to each other by a finite number of steps of adding or subtracting the boundary of a rectangle So let's draw a picture to illustrate this one. So suppose you had 2 points here, here, and you had 2 polygonal paths consisting of only horizontal and vertical sides. For example, this one, it can be very rare. Okay. And second one probably is this one, just this one. And since our domain is U, is this one. It's inside. Okay, so the second sentence in particular means that from the red one to the green one, we can do the transformation by adding or subtracting so finite many boundaries or rectangles. For example, this one, you cut it into a small piece. Okay, so here, let's denote this by green 1, green 2, green 3, green 4, green 5, green 6, green 7, green 8, and the direction is go from point A to point B. And here, similarly, you have red 1, red 2, red 3, red 4, red 5, red 6, red 7, red 8, etc. And the direction is goes this way. And also here you had the actual accelerate size. So for example, this one, let's call it go from this way. Let's call H1, and this one H2. So we take the direction goes like this: H4, H5, H6, H7, H8, H9, H10. Okay, now let's see. We have R1 plus R2 plus R3 plus H1 minus G1 is let's use different color. Plus H1 minus G1 is the boundary of this. Is oriented boundary of the rectangle. Let's call it blue 1. And similarly, we have R4 plus H2 plus H3 plus minus G2 minus H1 is the boundary, so oriented. So here the orientation is clockwise. It doesn't matter, but you need to make it the same orientation. Okay, it's a boundary of, let's call this one B2. Is a boundary of B2. Okay, similarly, you can construct small blue rectangles as B1 and B2. And then the tricky part is, so when you sum up the oriented boundaries of all the small rectangles, that means B1, B2, and here actually you have, this is B3, B4, B5, B6. Okay, and here you can cut into smaller pieces. 7, 8, 9, 10, 11, 12, 13. Yeah, I leave it to you to construct for this diagram, this picture, and sum up. We have R1, so we use this notation. On this side, you have minus boundary B1 minus, because usually when we take a boundary, we use counterclockwise. So here, since our orientation is clockwise, we reverse it. We have minus sign. And the other side, what do you have? So you have so first the red part, and then you have the green part, and then in your formulas you have the colorful part, but then the most important thing is for the colorful part, you have cancellation. You count those colorful parts appear twice, and the one with positive orientation, the other one with negative orientation, or the reverse orientation. So finally, if you sum up all the small rectangles, they cancel out. So you don't have this one. So what does that mean? That means when you do all this summation, you have, this is red path, minus green path. So you transform the red path to green path by subtracting or adding some boundaries of the rectangles. Oh, sorry. So here, actually, you need to look at the picture carefully. Sometimes you might have positive sign. Sometimes you might have negative sign corresponding to subtracting or adding. So I leave it to you. So leave it to you to construct for this particular picture. Yeah, as I said last time, I think the most difficult part when you generalize the special case Goursat theorem to the general case Goursat theorem is topology. You need to have a little bit imagination to see how you manipulate the topology in 2D. In 3D, it becomes more and more complicated. It's a huge field. It's called low-dimensional topology or three-dimensional topology. You need to have some hyperbolic geometry, group theory, conformal mapping, complex analysis, dynamic system to study it, even some intuition from physics. And for 2D, relatively complete understood by generations of mathematicians, but you still need to have some hard time. You will have a hard time at the very beginning to get familiar with this. Okay, so I suggest you to spend time on the topology, especially on this example. So the strategy actually here hidden and at the back is we want to transform the topology problem to a combinatorial one. That's usually sometimes a fancy name is called discretization. So you want to make some continuous stuff to some discrete stuff so that the computer can manipulate or human being can manipulate. So here we transform, so first you see we transform an arbitrary path we narrow down to some polygonal paths which consists of only horizontal or vertical side. So that's the first step. Second step, you just cut it to finer pieces such that they are the boundary of some rectangle. Okay, you have smaller rectangles. They have bunch of boundaries, and then if you sum them up in the correct with the correct sign, then you turn back to the original problem. So this is second time we use the idea, and later on when you study the Riemann surface, which is a generalization of the complex plane, if you don't want to, you just think about you have a surface in R3 embedded, closed surface with no boundary. So how to study it? A usual way is you put a bunch of points on it, and then you do triangulation. So each small one is a curved triangle. Then you can use some combinatorial way to study it. And even behind the complex analysis, a basic idea is we want to sometimes mimic what we did for polynomial to the power series. So it's also kind of discretization. Okay, and the remark two is the primitive is pretty much like the real case fx, and then you want to find the primitive. In 2D, of course, you cannot always do this, but fortunately, since we assume f is holomorphic, then we can do this in the holomorphic category. Okay, and if you want to learn more, the sufficient condition, necessary and sufficient condition, is actually called Poincare lemma. So suppose you have a M form omega, and then how to find a M minus 1 form omega such that d omega is omega. Okay, so there's a sufficient necessary condition, that is d omega must be 0. And it's also sufficient locally, but globally we have some abstraction which is called the homology or cohomology equivalently. So I will not spend time on this, but I just want to say, so why, think about the real case, why we always can do this locally, because here fx dx is a one form omega, and the d omega, whatever it is dx wedge dx, which is 0 by the anti-commutativity of the wedge product. Okay, but then you can verify that in 2D this is no more true. In 2D, fxy dx or dy, you take the wedge, you take the exterior differentiation, you have partial y partial y dy dx. It's not 0. Okay, so a little bit more complicated. Okay, next let's prove this corollary as a first step towards a general Goursat theorem. So define fz as a integral of fz dz along any polygonal path inside U, joint z0 to z in U with only horizontal and vertical sides. And since it's simply connected, then we can use remark 1 introduced here, discussed here, and by remark 1, and the special case of Goursat's theorem for rectangles. Okay, the function capital Fz is well defined. so which is a independent of the choice of the polygonal path inside you connecting z0 to z. So why? This is because so you fix point z0 and you view the upper limit as your variable. So that's the definition of capital Fz. Of course, just like in the real case, the primitive can differ by constant. Suppose you have two primitive f1, capital F1 and capital F2, then capital F1 minus capital F2 must be a constant. So without loss of generality, we can choose F to be this one. And so here along red path and so F hat, suppose you have two paths. So this is just a line integral along green path. Then Fz minus F hat Z is red path. G. It's gamma G, gamma R. Minus gamma G. So integrand is still F c C, D c C. Okay, and by the remark, you can decompose it to some small rectangles, and then the summation is summation rectangle BI and integration along the boundary BI. Of course, you might adding or subtracting. So here you have positive or minus sign. And inside you have F c C, D c C. So this is by remark 1. Okay, then this is 0 by special case. Goursat. Because for each small rectangle, we know the integration along the boundary is 0. Okay. Then the first step is done. Fd is well defined, which is independent of your choice of the path. Okay, but here actually I will remind you that rigorously here I ignore some subtle issue, that is remark 3. We should make sure the small rectangle BI is inside U. So what does that mean? That means your domain might be like this, or Let me draw a weird one. And then the path might be like this. Okay, so for example here, so you cannot take your rectangle to be this one. Not allowed. Because you want your function to be well defined in each small rectangle. So how to deal with that? So don't worry. So the only thing you need to use is cut the rectangle to small pieces. So since the red path and the green path are compact, they have positive distance epsilon to the complement of the domain. Okay, and if we take BI to have a length or the size less than epsilon strictly, then we can make sure that each BI is inside U. If it's not inside U, you can just drop it. It doesn't affect your computation. You also take time to think about it. It's not the main issue of the proof, but give you a good view how complicated the topology might be. Okay, later I will make another remark which is subtle but not a main topic for this course. Okay, next let's finish the proof of the corollary. So here we define capital F. Next thing we need to verify claim Fz is holomorphic, and therefore you can take the complex derivative, and then F prime is Fz. So here we need to take derivative and the things the holomorphic function small f is is continuous at least, and then therefore the capital F, because it's an integration, is differentiable. You can take a derivative. Okay, so think about it. So now let's fix or take an arbitrary point x0. Arbitrary point. Let's change z theta in U. So by adding to the polygonal path, joining z0 to z hat to the hat horizontal side whose left endpoint is z theta and and whose right endpoint is z theta plus h. So here h is a real number, and z theta plus h, make sure this is also a point in U. So what do we have? Actually, inside a simply connected domain, probably like this one, and you have z0 somewhere here, and z theta here. And of course, you can draw a polygonal path such that the capital FZ is well defined. Now, you take a new path from z theta to z theta plus h. And then you see by the previous argument, we know that f z theta plus h minus f z theta is integration along this horizontal line. Let's call it L. F ker C, D ker C. Okay, this is true for any h and such that h is real, z theta plus h is in U. Okay, now let's parameterize it. So this can be written down as from 0 to h f. Okay, so let's step by step. Z theta plus h, z theta dz d ker C, sorry. Now let's change the variable. So let ker C be 0 plus z theta, sorry, plus t, where t is a real number. So here you will have from 0 to h f z theta plus h plus t dt. Okay, now the derivative, the x derivative of f z at z equals z theta. What is this? This is by definition limit h goes to 0, f z theta plus h minus f z theta divided by h, which is without loss of generality, we can assume h is positive. dt divided by h. Okay, since small f is at least continuous, then the limit gives you Fz theta. Similarly, you can compute y derivative. So here, the only difference is that still similar picture. Now you adding a vertical line to it. Z theta plus h, and then equals limit h goes to 0 plus f z theta plus I h minus, here, let's still take h to be a real number, but then the point near z theta will be z theta plus I h. The imaginary part is h. H, and then you have, the reason I carry out a similar computation is because I want to tell you how do we get the actual I factor. Okay, limit h goes to 0 plus, and then the integration from z theta plus I h f c c d c c. And now we let c to be z theta plus it. Then when you change the variable, here you have 0 to h f z theta plus I t d I t. Okay, then you have actual I times f z theta. Then first we can verify the since here capital F is differentiable, real differentiable, we can apply the first definition of holomorphic function, which guarantee the second definition. So we compute the Cauchy-Riemann operator acting on F, and this will be F plus I times I f z theta, which is 0 constantly for any z theta in U. Therefore, capital F is holomorphic according to first definition. Of course, it's holomorphic according to the second definition. And then what's the derivative? So recall that the derivative, complex derivative, is a linear combination of the real derivative as following. And then if you compute it, this is just fz. So we are done. Okay, next we can prove the general case of the Goursat theorem. So first, assume the step 1. Assume the given open neighborhood U is simply connected. Then, by the above corollary, there exists a parameter fz for small f on U. Notice that just a remark, small remark here, the parameter is not unique, but different choice only differs in a constant, differs by a constant. Okay, notice that the integral of fz dz over any piecewise actually don't need, it's not necessary to be piecewise, but for simplicity, piecewise smooth path in U is equal to the difference of the values of capital F at two endpoints. This is kind of like Newton-Leibniz rule. Okay. Moreover, the boundary of U, boundary of omega consists of several pieces of closed paths. Recall, we assume that you have a domain U where your function is defined, and inside you have a subdomain omega which has smooth boundary, piecewise smooth boundary. Okay, then you have several pieces, but each piece is a closed loop. So the integration of small f along each small loop is 0. Therefore, integration of f along the boundaries of omega is 0. Okay, so the first step and the assumption U is simply connected. So step 2, we want to remove the assumption U is simply connected. Here we have some other tedious tedious issue of the topology. So I won't prove in full details, but I will give you some idea how we proceed. So step 2, the reason I won't give the very rigorous proof is that we won't use that in our course in reality. Actually, all we have either is concrete or just 2 pieces. Okay. So step 2, suppose you had domain U. It might be bounded or non-bounded, doesn't matter. Then in 2D, in 3D, it's more complicated, and you cannot just do this. The difference between 2D and 3D is huge. Okay, so your domain is a region subtracting certain holes. Those holes might not be circle or might not be disk, can have very weird shape, but they have a piecewise smooth boundary. Okay, then you can verify it's, of course, it's not simply connected. For example, as we shown before, this curve cannot be shrunk to a point. Okay, so the idea we deal with this is we cut the domain into several pieces such that each piece is simply connected. Okay, so for example, you can call this one. So you go this way, this way, this way, this way, this way. Let's call this L1. And then so if you go this way, this way, this way, this way, so the enclosed region, let's call this L2. Okay, similarly you have L3, L4, L5, L6, blah blah. And then for each Li, it's simply connected. You can apply the previous case. So the step one, the result in step one, and sum them up, you will get a result. So let's write down the argument roughly. So we choose a finite number of line segments, gamma 1 to gamma p in omega, transversal to the boundary partial omega. The reason why we want to be transversal because we still want the smoothness. Okay, if it's not transversal, you cannot say that the cutting is nice. Probably you might have this case. So you have a curve like this, and then you might have this. So the cutting is not so nice. You don't know how to take it to finite pieces. Okay, so think about it. Why transversal? Okay, with endpoints in the smooth part of partial omega, such that omega minus all these curves are simply connected. But of course, it's not connected because after you take off all the green line segments, you have disconnect piece. L1, you cannot find a curve from L1 to L2. Okay. And for each epsilon greater than 0, let gamma j epsilon be the set of points in C with distance less than omega for from Rj, and let omega epsilon equals omega minus j from 1 to p gamma j epsilon. So here the procedure is you just shrink the green part a little bit, or you thicken the green part a little bit. So here, so this, so if you don't want this, don't want to know the tedious part of the topology, you can just skip what I said in the following. So you thicken the green part a little bit. With distance epsilon. So now if you get out of the second green part, then you have pieces here. Okay, it's a little bit nicer, and probably you can just use the original one, but I guess you might have some topological issue. Okay, so we have integration along the boundary of partial omega epsilon fz dz equals 0, then let epsilon goes to 0. We have partial omega fz dz equals 0. It's not, as I said, it's not so rigorous, but I hope you can get the idea. And in reality, we don't need to use this argument because always we have a concrete description of the domain omega. Then you can just manually cut it and prove one by one, as what we did in step 1. Okay. And a small remark before we end up with this lecture should be remark 4. The condition of the boundary omega can be weakened to rectifiable Jordan curves. Several. You can drop the smoothness assumption on that as soon as you can compute the length of the boundary. Okay, I can't remember, but when I was an undergraduate student, I read the proof for this one in some Chinese guy's paper dating back probably 1940. But to be honest, nobody will use the weaker case. Okay, as well when when you need the weaker case, actually you are doing some very subtle analysis of the topology. Then you have a huge machinery to study and to learn in that specific topic. That's not purpose of this course. I guess most of us in this class will not need that in their whole life. Okay, and yeah, so the point I want to make is whenever you study some subject, the first thing as a beginner you need to know is the most special, most distinction part, crucial part, main ingredients of that topic with some concrete example instead of pursuing the most general case, most fancy stuff, most complete result. It's not the best way to do that. We for example, we can formulate the differentiability of a function, how smooth it is, when this is first, when it has first derivative, when it has second derivative, or whatever. People do study a lot on this, probably in 19th century, but it turns out nowadays nobody care about this. We have real analysis. That's enough for our use. Okay, I will stop here. Next time we will apply this to the most interesting case, the Cauchy integral formula, and then we can expand the holomorph function into power series locally.